Hi, Yongji, how are you doing?
I'm good,
Hi,
thanks a
Danyang.
lot.
Hi, wonderful. Hi, Danyang.
Hey, how are you?
Hey,
Hey, how are you doing? Good, good. So, I think it's already 11:01, so we can get started because we are not we are essentially we are doing things on three platforms. We are doing our presenting and discussion on Zoom. And in the meantime, we have a Tencent meeting and also a video streaming website, a platform in China to rebroadcasting. So while people are joining, I think we can get started. We typically have around the 25, 30 people joining on Zoom, and approximately the same number on Tencent meeting. But for the video streaming, we don't know. We usually don't keep keep head. We usually didn't keep count on that. So, but I think we can get started. Uh, So for everyone who has been in our meeting before or the first timers, my name is Xiang, and I'm the organizer for the SIGCOMM Paper Reading Group, and this is our 12th meeting. Uh, so in this meeting, we will together to continue our journey on to continue our journey on machine learning system. In particular, we will focus on the collective communication libraries in machine learning system, but different from previous studied what we have studied like Crooks from Alibaba, who focus on the scheduling, the global scheduling for Alibaba its own infrastructures. But this week we will focus on a multi-tenant cloud, basically how to do efficient collective communications in the setting of a cloud platform with multiple tenants in place. So in other words, the tenant only lease the resources. They don't have, they do not know the underlying physical underlying physical topology or detailed as informations, right? So at least that's my very basic understanding. So to solve that, design efficient collective communication uh, solutions for these settings. And Yongji Wu and Danyang and several other people from Duke and Meta work together to design a system called MCCS. So then that's what we are going to read together. So it was published in SIGCOMM 24. The title is called A Service-Based Approach to Collective Communications for Multi-Tenant Cloud. So for our meetings, as usual, we will have one student to present who is not an author to present this paper because we want give students, volunteers, an opportunity to present papers. So basically, it's a learning experience. So this week's presenter will be Yuntao Zhao, who is an incoming PhD student at Xiamen University, and and Yuntao will do make the presentation using about 25 or 30 minutes, and after that, we will Qiang, who is also assistant professor at Xiamen University, will host the discussion with Danyang and Yongji, and we will in the meantime we will take the questions from the audience. All right, so I think and after this very brief introduction on what we will be reading together this week and who will do the presentation and who will join the discussion, we will move on to the first item. Yuntao, you can have the floor to make your presentation. Thanks.
okay. Hello, everyone. I'm Yuntao Zhao, an incoming PhD student at Xiamen University. Today, I will be presenting the SIGCOMM 2024 paper titled MCCS, a survey-based approach to collective communication for multi-tenant cloud, authored by researchers from Duke University and Meta. Today, collective communication has become the de facto method for synchronizing data among workers during the distributed training of machine learning models with various parallelization strategies. For instance, in data parallel training, gradients from all workers are accumulated using the all-reduced collective. In all-reduced, data buffers from all GPUs are reduced. and the results are written to a user-specified receive buffer on every GPU. According to a report, collective communication takes up to 42% of the overall training time of common large language models in a TPU cluster. So, as a result, improving the performance of collective communication has always been a key research topic. Currently, all collective communication is implemented through libraries. This library provides a common collective communication primitive, such as all reduce and all gather. First, the application links with the collective communication library at compile time. And at runtime, the collective communication library determines the collective strategy. For instance, whether to use a ring-based or tree-based algorithm based on some static rules such as the data size, the number of GPUs, and the types of interconnects between them. Now, typically collective communication libraries include Nico, Rico, and Hico. However, distributed workloads have increasingly moved to the cloud for easier infrastructure management and better resource pooling. And in such multi-tenant cloud environments, the traditional library-based approach will encounter many problems. First, as I mentioned earlier, to optimize the performance of collective communication libraries typically select the optimal collective strategies based on certain network properties, such as topology. However, this information is not available to cloud tenants. For security and privacy reasons, cloud providers are usually reluctant to disclose their topology and other information to tenants. This lack of visibility into the physical topology can lead to suboptimal collective algorithm select or configuration. For example, in ring-based collective algorithms, where data transfer follows workers' ranks, which are assigned by users. Without this topology information, randomly assigning ranks to workers in different ranks could lead to the ring crossing ranks back and forth multiple times, and hence it causing significant more inter-rank traffic than necessary. The figure here shows a production transformer, where we show a drops ratio of cross-rack flows compared to the optimal one and the drop size. A bad ring ordering results in 2 times cross-rack flows, and the overhead becomes more significant as the drop scales. And second, current libraries decide the exact state and initialization time, and will not change the chosen strategy once the drop starts. While this is fine for single tenant settings, it's not ideal for multi-tenant settings. In multi-tenant cloud networks, background traffic may change the network utilization, or new tenant application may arrive. So the optimal collective strategy can dynamically change due to these factors. And third, current library-based approaches are also unable to enforce policies such as flow scheduling and traffic control. For example, we may want to prioritize serving workloads over training workloads. The root cause of these issues lies in the fundamental limitations of the library-based approach when facing multi-tenant cloud networks. On the one hand, the collective communication library is only loosely connected with the cluster topology and is completely disconnected from the workloads of other tenants. This results in a significant loss of optimization opportunities. On the other hand, there is a strong coupling between each application and the collective communication library, which prevents us from dynamically dynamically changing the collective stage and its implement. Therefore, the paper argues for an alternative architecture where collective communication is provided as a service by the infrastructure owner. Our architecture, MCCS, Managed Collective Communication Service, is shown in the figure on the right. In MCCS architecture, collective communication is directly integrated into the cloud network and provided as a service. A shim library is linked into the user applications. Unlike traditional collective communication libraries, the implementation of the collectives is decoupled from it. The shim library connects to an MCCS service and communicates with it through a shared CPU memory queue and GPU buffers. The single MCCS service is persistent on the system and shared across all applications. So with such a service-based collective communication, we can jointly optimize multiple applications' higher-level collective strategies, as well as lower-level network scheduling. We can also enforce some queues policies between different tenants applications, among many other new opportunities. Still, implementing such architecture is not trivial. There are several challenges we need to address. First, how can we decouple collective from the application while maintaining similar collective APIs as the library-based approach? And second, how can we dynamically reconfigure collective strategies at the application's runtime with minimal overhead? And finally, how can we flexibly support scheduling policies at different levels? First, in Nico's collective interface, let's take altogether for example. Users specify send and receive buffers, message size, and which CUDA streams to include the operation on. In order to maintain a similar interface, we must first address the memory management problems. Both the MCCS service and the application must have access to the send and receive GPU buffers specified by the users. However, GPU memory is by default isolated between processes. The second problem is about synchronization. CUDA streams are similar to CPU threads, where operations on a CUDA streams are sequentially executed. MCCS must maintain a CUDA stream semantics as in Nico, where when the user calls a collective API on the CPU, it just simply includes the collective to the user specified CUDA stream. Let's first look at our solution to memory management. The paper addresses the memory management challenge by choosing to redirect control over GPU memory allocation and deallocation to the MCCS service. Specifically, in MCCS, users allocate memory through the malloc API provided by MCCS instead of using the CUDA malloc API provided by CUDA. So when MCCS malloc is called by the user, the MCCS shim issues an allocation request to the MCCS service over the shared memory command queue between the application and the service. A dedicated front-end engine for the given application then will handle the request by allocating memory on the specified GPU device and obtaining an inter-process memory handles to share with the application. The MCCS shim receives and opens this handle to obtain the underlying device pointer to the allocated memory, which it returns to the application. So, with this IPC memory handle, the application can then freely use these pointers to invoke compute operation, while for collective operations, such as MCCS or Gather, the string sends an all-gather request to the MCCS service, passing the ID of memory region and the offset for both the send and the receive buffers. And this process flows similarly for the allocation request. The stream is responsibility for closing the IPC handle before forwarding the request to the MCCS for service. With the memory management problem solved, let's next look at the synchronization issues. MCCS addressed the synchronization challenge by designing an event-based mechanism that maintains the traditional sequence of CUDA streams, which enable the sequential ordering of dependent compute and collective operations. Specifically, during initialization, MCCS service pass an inter-process event to the MCCS string. For the string, the service used for executing collectives. On the other hand, for each user string, an inter-process event is created when the user invokes a collective on that string for the first time. The event is passed to the MCCS service. When executing collectives, these IPC events are used to synchronize between the application and MCCS service. The event primitives provides the ability to include a string operation that will block, waiting for the notification of an event that was included on a different string. So, for example, users issue an all-gather between two compute kernels on the same string. And the MCCS service string waits for the complication of the first compute kernel and only then conduct the all-gather. The user string also waits for the complication of all-gather before executing the second compute kernel. So, having addressed the key challenge of memory management and synchronization, we have successfully decoupled collective from application while maintaining similar APIs. Next, we focus on dynamic reconfiguration. While it is straightforward for all nodes to agree on a configuration at initial time, which necessarily takes place before collectives, this is much more challenging when implementing reconfigurations between collective operations. For an illusion of this, consider the example shown in figure. Here, we assume an application created a communicator consisting of n GPU and let's issue a series of all reduced collectives for that communicator. Since collectives are synchronized operation, all participating GPUs must use the same configuration. Let's say if we want to update the ring to a new order ring where the link between 0 and 1 is reversed. So a reconfiguration command is issued to all the n GPUs. However, due to arbitrary network and processing delays, it's possible for the command to arrive at GPUs 1 to n before the complication of all reduced 0. And the configuration of GPU 1 to n is updated to the new ring. However, the reconfiguration command arrives at GPU 0 only after all reduced 1 is issued. In this case, GPU 0 uses the old ring, while GPU 1 to n uses the new ring. So the all reduced hangs forever. This is a problem. So MCCS uses an all-gather based synchronization to solve this problem. Each node maintains a sequence number for the collective over time, which inherently match across all nodes in a communicator because each collective involves every node. So after the reconfiguration command arrives at each rank, An all-gather operation is first performed to collect the sequence number of the last launched collective. Local updates will not completed until the all-gather completes. So at this point, GPUs 1 to n will not perform any updates. The all-gather only completes after GPU 0 receives the reconfiguration command. And we determine that the last launched collective is all reduced 1. So nodes can use the secret number to identify which collective should precede any reconfiguration update. So MCCS still use the O-ring to complete all reduced 1. Only after all outstanding collectives are completed, the reconfiguration is updated to the new ring, and all collectives from now on use the new ring. The key takeaway of MCC's all-gather based synchronization is that it only happens during reconfiguration and does not introduce any overhead on the fast data path. Finally, we will demonstrate how MCCS can flexibly support scheduling policies at different levels. According to the architecture of MCCS, the MCCS service is controlled by a cloud provider and has topology awareness. So, at a higher level, we can choose different collective strategies, such as ring ordering used in ring-based algorithm. At a lower level, for every flow in the collective communication, the MCCS service can also decide its network path in the cloud network using source routing or other path control schemes, thereby scheduling the network resource. Further, the MCCS service can also enable fine-grained traffic control by controlling flow paths and the timing of collective communication operation execution. The first policy example is locality-aware ring configuration. The ordering of how the hosts are changed in the ring collective algorithm directly dictate the overall communication pattern. So to minimize the number of close-rack flows, MCCS applies a greedy algorithm to configure the ring ordering for each communicator based on topology information. The second policy example is best fit fair flow assignment. Once the ring configuration for all applications is optimized, the communication patterns between hosts and hence the set of flows can be determined. However, if we're using the standard ECMP approach to map flows into network routes could lead to significant overall collective performance degradation and inconsistency due to flow collision. So our goal is to maximize the aggregated collective performance of all applications and ensure fairness between different applications. Therefore, MCCS uses a slightly modified version of the greedy heuristic approach in Hedera, where for each flow we are assigning the path that has minimal excess bandwidth demand. The third policy example is priority flow assignment. MCCS modifies FFA to allow some routes to be reserved for high priority application. MCCS first feeds flows of low priority applications using only non-reserved routes, and the flows of high priority applications are assigned the best routes from all available ones. The last example is traffic scheduling. With priority flow assignment, we can dedicate the network links to some of the highest priority applications. However, we may still have some applications sharing links. MCCS can enforce a traffic schedule to control when each application can send out traffic. MCCS apply a simple time window-based approach inspired by Casny to interleave traffic. The transport engines in the MCCS service allow other application to send traffic only when the prioritized application is idle. So through this example, we can intuitively see that MCCS enable a joint optimization of algorithm strategy at a collective level and the flow assignment at a network layer. This example effectively illustrates MCC's system capabilities beyond what today's collective communication library can offer. With all the challenges solved, let's see how MCCS really performs. We have three objectives for evaluation. Can MCCS improve performance of a single application with topology-aware scheduling? Can MCCS improve performance of multiple applications with multi-tenant collaborative scheduling? And can MCCS quality of service capability benefit training workloads? In our evaluation for topology-aware collaborative scheduling, we explore two policies. The first is locality-aware ring configuration, where we optimize ring orderings to minimize cross-rex flows. We also adopt a flow-assigned algorithm based on heterodox to maximize the aggregated collective performance of all apps. We first evaluate single application all-gather performance on 8 GPUs, where each host has 2, and the host also has a 100 gigabits NIC for inter-host communication. The bandwidth on links between switch is 50 gigabits. Compared with vanilla NICO, MCCS achieves a speed up of 2.8 times. We also compared MCCS without the flow scheduling algorithm to a variant of NICO where we manually feed the optimal ring configuration to it. MCCS has negligible overhead on large messages, indicated by the similar performance between MCCS without flow scheduling and NICO with optimal ring algorithms. We can know that MCCS does have some overhead for smaller messages, which is caused by the multiple rounds of data passing in our current prototype. To evaluate multiple applications' performance, we placed 2 applications, each using 4 GPUs across all 4 hosts. Each GPU on the host can use half of the NIC bandwidth. In this case, MCCS also significantly boosts the performance of all applications, achieving a speed up of 2.5 times. To demonstrate MCC's cost capability, we explore 2 policies: a flow assignment-based one that reserves some routes for high-priority applications, and a fine-grained traffic scheduling one based on k-signer to prioritize high-priority applications traffic. We show the throughput of 3 training workloads, normalized to the values between T2 and T3. First, there is only drop A, and at T1, drop B arrives. At T2, drop C arrives. And this time, no policy is applied, so the performance of A is degraded. At T3, we prioritize A using priority flow assignment policy, which is improving A's throughput at the expense of B and C. And at T4, we further prioritize B over C or using the traffic scheduling policy. So MCCS again is effectively enforce such a quality of service policy. Thanks for listening.
Okay, yeah, thanks, Yuntao, for the presentation. I think it's very thorough, conveys the idea very clearly. And I think now after the presentation, I think Zhang, you will host the discussion with Danyang and Yongji, right?
Yeah, sure. Hi, Danyang. Hi, Yongji. I'm Chen from Xiamen University. And Yeah, this is a great work. And actually, I had a work which is about network stack as a service, and we shared the similar high level ideas. And yeah, this is cool. So does anybody online have any questions? So you can just say it or type it in the chat box. So let me just start with a very simple question. I think in the evaluation part for the single application, you said MCCS improve about 2.8 times performance improvement, and I think it is it comes from flow scheduling, right?
It comes from both parts, both the scheduling of the kind of algorithm as well as the network flows. So it's two parts.
Yeah, I got you, but considering that for small message sizes, the performance is not very good, right? So, Chen, do you have any solutions to optimize the performance in small message sizes?
The small message performance mainly as the optimization issue in our current prototype. I think that can be significantly improved actually. For at least yeah, if you're not considering very small message like several bytes, yeah, and
Several bytes.
yeah, and but I think yeah, it's mainly because we have multiple rounds of redundant message passing in our current prototype, and so we have some overhead for messages that is quite very small. And I think yeah, small messages is also less frequently used and contributes little to the overall running time. I think
Yeah,
of
that makes sense.
major ML applications.
Okay, so will that influence the start time, the start time of the Lico services?
What do you mean by start time?
Start time, the launch time.
You mean the launch time of kernels?
Yeah.
Yeah, because because currently the credible kernel will only be launched let's say after our backend receives a message, but it's basically it still launched asynchronously with the GPU's kernel execution. So basically the communication is still scheduled to the GPU kernel after we receive the command from the user application. Yeah, it basically still follows the equals the Q.stream semantic.
Okay. Yeah, I got you. Yeah, that's cool. So, I have another question. Does MCCS support adaptive collection communication policy optimization at runtime?
Yeah, we can definitely support that. And
Yeah.
I think our QS example is actually a showcase of how can we change the policies for each application dynamically.
So when there are, for example, many new applications, will there be any scalability issue? So, for example, the MCCS may have fixed the size of dedicated memory region, right?
I think the overhead basically comes from, let's say, if we want to have some control of all applications, we might want to use a centralized scheduling part. Actually, how can we configure each application is separate from the MCCS system. Yeah, and I think because if you are considering some normal training or inference job, I think their communication patterns are quite static, and basically you don't need very fine-grained control over the policies, right? You only need some coarse granularity reconfiguration when each application joins a disk. So I think this is the overhead. This overhead will not be significant.
So, in your experience, so how much overhead the MCCS service will
I remember we only have let's say source overhead less than 1 second for when reconfiguring application in our evaluation in the paper. Yeah. And this only happens, let's say, if a training job completes a new training job in the system.
So, following this question, in the scenario that there are both training applications and inference applications, so we know that inference applications are latency sensitive. So when co-running these kinds of applications, does MCCS will make the time of inference applications longer? So
actually, this is I think also a good use case for MCCS because in MCCS we actually provide whatever network administer with flexible policies choices, right? We can actually dedicate some network links to our network path to MCCS to the inference application, so to ensure their latency is minimized. And you cannot do it without MCCS actually in public cloud.
Chen, I have a couple of questions. If you if it's okay.
Yeah, I need some time to think of this. Yeah.
Sure, of course. So this is a very interesting work, but I think the based on my understanding and also the presentation of the paper, the motivation for MCCS is because basically the scenario here is multi-tenant cloud. Basically, the network is unwilling to expose the topology related information to the tenant, right? So I think my understanding is MCCS basically takes the other way around. Basically, we let the cloud provider to do the schedule to make the scheduling decisions. So I think I have like two questions. The first one is because I used to work on this concept called network information exposure. Basically, I worked with a few people in the IETF Auto application layer traffic optimization working group. So Auto for short, right? So the basic design for or the basic idea of Auto is is a set of is a protocol that expose network related information to applications, so that applications can make better decisions, right? So of course, there's always a trade-off between how accurate the information is exposed and how safe, quote unquote safe, the information exposed, the information exposure could be, right? So but there's always a question. I no longer have time to work with those people, but I remember there's one question we don't fully understand is how unsafe or how unsecure if we expose topology related information to applications. Is there like a quantitative study? I mean, as a provider, either cloud provider or ISPs, right? We always say, hey, we do not want to expose our information. We think that's a safety security, that there could be security issues. But I remember back at the day, I could be wrong, but I did do some literature research, but I couldn't find a very I couldn't find a very solid study about how to quantify the risk. Yongji and Danyang, do you have any insight on this?
I think the okay, Danyang, you go first.
Maybe yeah. First of all, thank you, Qiao, for organizing this event and inviting Yongji and I. I think this is a great event, and thanks Yuntao for the presentation. I think it's very comprehensive, and Sue for organizing this Q&A session. So I think there are some problem of exposing network information. I think today, because network performance is quite important in cloud workloads, basically the cloud provider want to optimize their network so that it does not block application, especially for distributed ML application, because it's a major bottleneck for distributed ML workloads.
Right.
Now the question is they may want to make the topology be a confidential information because they will be innovating on that. Another thing is a little bit tricky. For example, usually to make a decision like a collective communication, you not only need the topology, you also need some bandwidth information. And it's usage information. And it's a bit tricky in the following way. So if you report your link utilization to be very large, the problem is a cloud client will be afraid that the network is congested, and if I use this cloud, I cannot achieve great performance. But if the cloud provider report the utilization is very low, it basically means no one is using that cloud, and so it is a very tricky information for cloud provider to expose. It can hurt it both ways. So typically, in papers, you can rarely see paper reporting on network usage. So that's a very tricky number, to expose. Yeah. So I think and there's another anecdote is we basically submitted a paper called Net Hint to NSDI. And we get some reviewer comments about it. It's basically the reviewers believe this is basically the idea is the cloud provider may be able to expose some information to the client, so the client can change their collective communication rather than the reviewers basically telling us this is definitely not as secure. That's why we can different way. Yeah.
I see. Yeah, the reason I'm asking this approach is because like I said, I did work with those people about designing protocols which we believe could certainly preserve the private information of the network while it's still exposing information accurate enough to the applications. So I'm not doing advertisement because that's a paper we published 6-7 years ago. So, but what we did here is like this, right? So we definitely do not expose topology, and because one is not that's even though for some reason everyone thinks it's unsafe, but even though it's not clear how unsafe it is, but everyone thinks it is, right? So. But instead we abstract the bandwidth information in the network into a set of linear inequalities. So very simple example: we have two flows, and suppose two flows shares a bottleneck, and this bottleneck link is say 10 gigs per second. So the available the available bandwidth of these two flows is consumed by one inequality called x1 plus x2 less than or equal to 10 gigabits per second, right? But of course, if we do not have, if the provider can in addition can enforce additional inequality constraint phase, say for example, if they think we do not want to let these two flows get 10 gigs per second, we want to limit the sum as 5. They can also do that, right? So basically information becomes x1 plus x2 less than or equal to 5. Right. So this is the very basic abstraction. I think it's at the beginning we name it the routing state abstraction, RSA. So but later, yeah, I think we rename it called the resource state abstraction. So something like that, right? I need to clarify that I only play very small part in designing that abstraction. So but I do think that's a very it's a very clever way to do that. So basically, because we can, for each link we can have such such linear inequality, right? And after that, we say we have 10,000 links, then we have 10,000 linear inequalities. It could be too big, right? But we can, well, there's a polynomial time algorithm that can compress. But basically, this 10,000 linear inequality compose a feasible region in linear programming, right? So, but there's a polynomial time algorithm we can use to compress to find out the minimum number of linear inequalities that has the equivalent feasible region as this as the one composed of these 10,000 inequalities. So essentially, we call it routing state abstraction compression, right? So after the compression, we have a relative small number of linear inequalities, and using that, basically topology can be. There could be, but basically it's like solving a linear system, right? There could be many different possible solutions. So that's what the way we think could help preserve the private topology related information of the network. But of course, this design has its limitations because bandwidth information could be very dynamic, and also one assumption I neglect to mention a couple minutes ago is that they will assume the routing is given. But I think that in certain way this is doable, right? These limitations can in certain way it can be tolerated, right? So I think that, but of course, because I switched my focus on more on network verification, so I discontinued that line of work. But I think that could be something we can explore in designing more efficient collective communication services or workload scheduling algorithm, even in a multi-tenant cloud settings. I think that's why I raised this question. But I think what then you just said, it makes sense, right? So basically, there, even if there is no definite technical evidences preventing us to do that, but in economic or social aspects, cloud providers may be reluctant to do that. I think that makes sense too, right? So Yongji, so sorry, I'm taking the microphone too long, but Yongji, you have other comments related to this?
Oh yeah, I think that basically covers what I want to say. And I also want to point out that this is actually only one of only a part of our motivation for doing MCCS. We observe as for example, I think we have a figure in from Meta. So even in a private infrastructure scenario, you generally have let's say these application developers who train their ML models, they will misconfigure their, let's say, basically they will not use, they don't know how to use the optimal configuration for Nico, right? And I think MCCS can also help manage this.
Okay, gotcha. I mean, it's not that the one design option is definitely is always better than the other one, right? So, but it's just happens to in these settings. I mean, letting the cloud provider making decisions, it makes more sense in the current shape, right? Okay, gotcha. All right, so moving on to my second question. Now that we settled that, hey, we still would want the cloud provider to do that. So I noticed that because when I read the abstract of this paper, I immediately recall one paper from SIGCOMM 14 from J.K. Lee from HP. I think he was at HP Labs, and then he moved on to Barefoot and now Google. I forgot Google. I lost track. But in that SIGCOMM 14 paper, I noticed you also cited as reference 22 in your paper. It's called Application Bandwidth Guarantee in Data Center Networks. I think in that paper, what JK did is he designed a new abstraction. So let the basic way is to let the users or the basic applications to specify their communication patterns and also possible, if possible, bandwidth usages. And I think it's called like a traffic attendant. I forgot. I think it's called TAG. I forgot the full name, but it's essentially it's like a DAG, right? So to decide, hey, there a flow, there will be a certain traffic flows, and maybe even co-flows possible, and what's the end-to-end requirement, and then if the user or the application submits all these requirements to the cloud provider, and then the cloud provider has this somehow has a scheduling algorithm to do that. So the high level design is very similar. I would say similar, definitely different, but similar to the rationale is similar as MCCS. Basically, we let the cloud provider make the scheduling decisions. But the question is, say if we extend the tag abstraction from JK's SIGCOMM 14 papers, could we end up a better or equally good solutions as MCCS? Or in other words, what makes it difficult to extend that paper to machine learning or machine learning systems in multi-tenant cloud?
So I think there is one difference between a traditional communication, when you specify the communication requirement for a traditional application, you basically can specify it at a end-to-end level. Say node A wants to send how many bytes to node B, node B wants to send how many bytes to node C. Then you can have some scheduler schedule your flow, right? That it flows through the network without any network level bottleneck. I think the key, the new space the MCCS opens is that for certain workloads, there's a knobs in choosing how to do the point-to-point communication. For example, I just want to do or reduce between 8 nodes. I do not care if I do ring or reduce, or even with ring or reduce, which order I want to do the reduce. So I can choose between like A send to B, B send to C, C send to A, or A send to C, C send to B, B send to A. So basically what we are talking about is we move up this end-to-end, like point-to-point abstraction to a more collective communication opportunity. So we can have the system do more optimization beyond the flow scheduling. We can do choice of collective communication algorithm together with scheduling. Yeah, I think that's I feel the main opportunity and CCS pointed out. Yeah.
I see. So let me see if I understand correctly. So you basically the decision space or the space for decisions it's expanded. It goes beyond, like you said, goes beyond flow scheduling, but goes into the choice of different CCL and even possible endpoint selection. Right. So, but it's not. It's not a purely we have flows in flow demand, and we try to find the route and the scheduling, but we even need to define the endpoint, basically to define which flows we need to transmit. And I say, yeah, that makes sense to me. Yeah. I think because if we keep doing so, let me. So my understanding is if we choose to use if we try to extend JK's SIGCOMM 14 paper into this collective communications in multi-tenant cloud, we may end up getting into severe scalability problem. Scalability because scalability issue because the space for the decision space is too large for that method or for that design to work. So but using MCCS, I think basically but it simplifies the problem without sacrificing the performance.
I think it is definitely possible to extend that work to consider like collective communication strategy. It's actually I can see a way, these two work can be combined to do something. But my feeling is that the challenges we address in this paper needs to be addressed again. If we extend that work to consider features that MCCS has. Yeah. So yeah.
I see. Okay, yeah, I understand that. I think that's very cool. Yeah, I think that definitely makes me has a better understanding about both MCCS and the JK's paper. Yeah. Okay. So yeah. Sorry, I've been speaking too long, but I already have finished up my two questions. So Qiao, I think there's a question from the audience.
Yeah, sorry to interrupt. There is a question in the Zoom chat box. So,
I see.
Xuan is from Duke University, and his questions are about the jitter. So the first question is, do you expect jitter to become more severe as more tasks are added? And the second question is that is there any approximate range for the numbers of applications?
I think the data is mainly because you have multiple applications sharing the same network links. But I think because it's actually our QS policy is just a showcase of MCCS scheduling capability. Yeah, we just use some simple policies here. And in fact, I don't expect you to have, let's say, 1,000 applications or 10,000 applications sharing a same network link, right? That doesn't make sense at all. So I think this, we won't have a very significant this jitter scenario. And also, let's say for between time t, this is for between in figure 10. I think that's maybe Yuntao, you can put it the slides further down, little 2 pages. It's the QS thing. I think the QS. Yeah. So basically between time t4 and further on, we'll actually use a very simple time window based traffic scheduling. And in our current implementation is a very simple strategy. And if I believe if we use some more fine-grained, let's say, scheduling mechanism, this can be definitely addressed. Yeah, I think this part of what concrete algorithm we use for QS is actually up to the users, and is not it's just a show. We just use some simple policies to showcase MCCS capability here.
Okay, the following question.
I think in our current prototype, MCCS only handles flow control, and if you flow assignment, and if you have it definitely use to transfer the layers for, let's say, any congestion control. Yeah.
Yeah. Okay. I have a high level question, and now that the collective communication becomes a cloud service, would it be possible to charge for this collective communication service? So either would it be possible to have billing strategies for different tenants?
I assume that's definitely good motivation, I think, for cloud providers to implement MCCS, right? You can, for example, if you have highly prioritized workload, just want to pay significantly more, you can have dedicated network links reserves for that.
Yeah, so I know that now the charging model of GPU clusters is mostly based on the GPU resources, right? But actually the cloud spend many network resources on the infrastructure. So yeah, I totally agree with you. The cloud providers would like to earn more money on the network resources. Yeah, so cool. I think this is around the end of our discussion. So now it is 12 o'clock. So yeah, thanks very much for discussing this great work. And I actually learned a lot of from this paper and the presentation. So Chao, now let's give the floor to Chao right now.
You want okay? You can just conclude the meeting, right? So yeah, because since Chen is my new colleague, so and he's also very interested in doing this, so we decided to take turns. You know, I take the easy part, and he takes the hard part. So yeah, but really like Chen said, that this is a very interesting paper. Certainly gives me a lot to think about and to chew on. And also, I want to thank Yongji and Danyang for taking the time to attend this group, a reading group. And it's really important for us to not only just read the paper and understand it by ourselves, but also to have you guys as authors to provide the unique insights of these papers. I think it's really very valuable for all of us. Yeah, that's wonderful. So
yeah.
So but as Xiang said, even though I'm sure we have much to discuss, but we probably have to take it offline. But so because we are already 2 minutes past our original schedule, so but let's thank Danyang and Yongji and Yuntao again for the discussion and the presentation. It's very interesting, and so this concludes our 12th meeting of our SIGCOMM Paper Reading Group, and we hope to see many of you again in 2 weeks.
Yeah, thanks for inviting us.
Yeah. Oh, definitely. Yeah, thanks, Danyang. Thanks, Yingyi. Thank you so much. Thanks, Yuntao.
Have a nice day.
Bye.